Jean-Noel Roux, who has changed his title slightly, I see, to Concentrated Non-Brownian Suspensions in Viscous Fluids, Numerical Simulation Results, a Granular Point of View. Okay, thank you. I had
Okay. Am I? Yeah. Looks like it's working. So I'm very thankful to the organizers for inviting me here, and I chose this theme, which is, I think we're all convinced of it, which is a sort of a frontier in granular material studies from a microscoping point of view. Quite a few of us are willing to introduce fluid between the grains. So that makes things, and especially in the numerical approaches, this makes things more complicated. And I wish I had more results to show to you today, but I was confronted with the same difficulties as the other people. So well, I have a few results that I will show, and that will possibly foster, hopefully foster discussion among us. We've been studying granular materials from a micromechanical point of view and relying a lot on numerical simulation for some time in our group and in the community. So this is work done in collaboration with François Chevoir, who is here, and with current and previous PhD students and postdocs at Laboratoire Navier, okay, which is the joint laboratory between. Well, I think my name comes with the reference IFSTAR. It's a Civil Engineering Institute, depending on the government, and Laboratoire Navier is sort of a joint laboratory, joint research unit, also depending on CNRS. Okay, in those studies of granular materials, we've investigated a lot their quasi-static mechanical response as probed typically and gradually applying a shear stress, an increasing shear stress, or maybe perhaps imposing a very small shear rate on an initial equilibrated state, typically isotropically equilibrated state. And we've also studied for some time steady shear flow with some inertial effects. This has been discussed by in several presentations yesterday and today. And now we're willing, also this is also an approach illustrated by several other speakers, we're willing to extend these approaches to dense suspensions. Dense suspensions look like granular materials. We have large hydrodynamic forces where grains approach one another. This is due to the lubrication effect that will be discussed a little bit in this talk later on. And this looks like a network of contacts, and actually grains might even touch within the fluid. So we have a kind of contact network, and it's a natural attempt to try and apply the same approach as in the dry granular case. Now, there are a few things we learned from our studies of granular materials, and one very interesting observation or very interesting concept is that of the so-called critical state. The critical state is the steady homogeneous state of a granular material that is being deformed in the same direction, for instance sheared at large strain in quasi-static conditions. And it turns out this is a concept that was actually, one can say, discovered and popularized from research done here in Cambridge, not in the math department, in the engineering department in Cambridge, critical states theory. And it proved very fruitful. And what we actually, it's behind what I'm going to tell you today, in fact. Here it's an illustration. It's not, oh, sorry, I have to be careful with that. It's actually not a simple shear test. The simple shear configuration is what I'll be discussing in the following of my talk. Well, it's somewhat analogous. It's what you more spontaneously do in geomechanics labs or in soil mechanics labs. You impose a so-called triaxial, axisymmetric triaxial compression. So you increase the stress sigma 1 while sigma 2 equal to sigma 3 on the lateral walls are kept constant. And so a sand sample or granular material sample, and in the case of those results, a sample made of spherical beads and studied by numerical simulation, will deform, and this is the deviator stress, which is quite analogous to, it's in fact a shear stress. Q is sigma 1 minus sigma 3, normalized by sigma 3, and this is what we see for the stress evolving as a function of the vertical, or in that case, the so-called axial strain. Now the dense sample will do this, the loose sample will do that, intermediate sample has this curve here, and they all reach a kind of plastic plateau that for which the stress is not sensitive to the initial state of the system, which was in that case varying by its density, and which does not, it's a quasi-static, maintained plastic deformation going on. Meanwhile, other variables like the density, solid fraction, here to be read on the right axis here, also approaches a limit that does not depend on the initial situation. So the existence of this flow structure is an important thing to know about, because it will be the reference state compared to which we will discuss different kinds of flows. This is the limit of quasi-static flow. Now, the characteristics of this critical state, this is not a complete one, but this is a compilation of a variety of numerical results, both in 2 and 3 dimensions. So this is the internal friction coefficient, so the ratio of the shear stress or deviator stress to the normal stress. In that case, well, it was the spherical part of the stress tensor, and on the one hand, and the critical density, the solid fraction in this state, on the other hand, while do not depend on many details of the granular material. They do not depend on the initial state, as we already saw. They mainly depend if the particles are not too soft, if they have ordinary stiffness level compared to the stress level that is applied to the system. They mainly depend on friction. They might also depend on rolling friction. Here, this is sliding friction. And oops, little step here. Okay, and there's an internal friction, macroscopic friction, in the absence of intergranular friction, and then we have this variation with contact friction between the grains, and the critical density coincides with the random close packing density if the particles are frictionless, and it is smaller if the particles have friction. Okay. Now, among the things we learned from studies of dry grains, and that will have an interest in the study of very dense suspensions. So we have this critical state concept with its flow structure. This is actually the minimum solid fraction to flow. So this is one kind of jamming, if you wish, but it's the one you see if you're interested in response to shear. We have the importance of the friction coefficient in the contacts to determine this quasi-static state, quasi-static critical state. We have the, well, I won't comment this any longer, but this is important. We have the strong influence of a rolling friction that might exist in intergranular contacts. It's quite influential and might exist in suspensions as well. And we know what the rigid limit is. We can quantify it with a suitable dimension S parameter. We just compare the stiffness of the contacts to the applied pressure. And now the characterization and study of inertial flows I've been involved in under controlled normal stress rather than fixed density can be seen as just a kind of generalization of this critical state in a situation in which the flow is a little bit faster, so we do see inertial effects. We're no longer quasi-static. So the idea is to use then an internal friction mu star, internal friction coefficient, as an alternative to viscosity. Now we're going to focus on steady uniform shear flows as depicted schematically on this figure here. We've seen this quite a few times already in this conference. So what I will refer to loosely as P is rather the normal stress sigma 2, 2. 2 is the direction of the gradient, axis 1 is the direction of the flow, and well, we impose gamma dot like this. And we're interested in systems in which there are contacts and maybe what I will call quasi-contacts, that is to say forces transmitted by a thin fluid layer. Now, there is the rheology approach, now referred to as mu of I rheology. So this is a quick illustration. Let's try to go fast over it. It's illustrated here by simulations done with frictionless beads with Pierre-Emmanuel Pénaud. And well, this is how we characterize the rheology. We measure effective internal friction coefficient versus inertial number I, as well as the density, solid fraction versus I, so nothing new. And this I number is this combination in 2 dimensions or that in 3 dimensions with A, the bead diameter, the particle diameter. Now, we've already seen in this conference that this approach was used to formulate, to define constitutive laws in 3D that might be applied to various geometries. Here, well, Olivier Pouliquin, Pierre Job did this, and also Lydie Staron saw this yesterday. Now, let's go to other observations. This one I like to show, these figures, I like to show them just to insist on how much more convenient it is to use constant normal pressure in shear flow than constant density. What we did here it's the same system, an assembly of frictionless spheres as on the last as on the last slide. We here started by applying constant normal stress equal to 1 in those units, while so this is the normal stress axis, this is the solid fraction axis. While the solid fraction fluctuates, it is measured, it fluctuates around the an average a little below 0.639. And we try to measure mu star. So there are fluctuations, but there is an average, and this is our macroscopic friction coefficient. And now, at some point, this axis is time, or better said, it's strain gamma, shear strain gamma. At 1 here, we switch control and we decide to keep the density fixed. So we we have measured its average. Density now is fixed at its previous average value. And meanwhile, this is the alternative approach. This is equally right, of course. Meanwhile, we measure the normal stress, but the normal stress does this. While previously the density was fluctuating by a small amount, now the normal stress, if we try to really study constant density flow, it fluctuates between 0 and 4. So measuring an average, which should be 1, measuring an average is a lot more complicated. But now if we measure this first observation, constant normal pressure is much more convenient. Now, second observation here is that if we measure the ratio, not one stress component, but the ratio of shear stress to normal stress, that is to say we measure the friction coefficient, we don't see anything changing here. So it means that both stress components fluctuate while being strongly correlated, so that the ratio is roughly constant, or a little bit fluctuating. So this quantity is what conveniently expresses the rheology of the material. That's just a reminder of that. Now, if we turn to dense suspensions, we can look over the literature. And the first observation to be made, I think, is that the numerical studies of suspensions, while numerical simulations of dry granular materials was making dramatic progresses, simulations of suspensions were very much lagging behind. And it's still very difficult, apparently, technically, to simulate suspensions, especially dense ones. So with spheres, there is virtually nothing above 60% solid fraction. Also, you see funny tricks, because in the abstract of the paper, the authors tell you, well, we're simulating dense suspensions of rigid spheres, and that's all. But inside the paper, you realize that they add funny little forces to prevent particles from overlapping or approaching too much. There are very few published results with above 1,000 grains, whereas with dry granular materials you have tens of thousands or hundreds of thousands nowadays. So this is a sharp contrast with simulations of dry grains. What makes the situation difficult is those strong hydrodynamic interactions. One of the things that makes the situation difficult is those strong numerical hydrodynamic interactions between grains that are close to one another, and so the lubrication singularities. And in the literature of 15 years ago or 10 years ago, they were believed to cause some funny dynamic jamming phenomenon below the maximum concentration of frictionless spheres, which is the random close packing 64% value. And this was more or less believed, I think, this is my impression on reading the papers, to be a possible origin of shear thickening in dense suspensions, formation of the so-called hydroclusters. And so those studies by Ball and Melrose, which we have followed in our own numerical simulation investigations of those systems, over that period of time, this is not birth and death of Ball and Melrose, just the first and the last paper I'm aware of on the issue, while claimed that due to those lubrication singularities, we have very singular effects, and we have actually no steady state. So, well, here, when I came to study this problem, I decided, of course, I wanted to solve those mysteries and to successfully tackle the numerical study of suspensions, which, of course, was partly a failure. But at least the introduction of controlled normal stress rather than controlled fixed density and some other ingredients I will present in a while did help. And also, I think the inspiration brought from previous knowledge of how dry granular materials behave. Now, meanwhile, experiments on dense suspensions, well, made more progress than simulations. We now have quite a few studies, experimental studies, which I will not review, but paying attention to density and homogeneities. And so now we have local measurements. We know exactly which is the value of this viscosity corresponding to which value of the density. Whereas in previous studies, when you just had the average concentration within the rheometer, it's not guaranteed at all that the system is homogeneous, as we saw in the presentation by Patrick Snabre. So, and we also have this recent paper in which the approach constant normal stress was, this was already cited in the talk by Martin Trulson yesterday. They also use this control of particle pressure, perhaps more successfully than in simulations. So we also get results, and we can, of course, it's natural to want to check if we can obtain similar, compare results of simulations to those experimental results, which are now making significant progress. And so the model is the following. We consider that the fluid is limited to near-neighbor gaps, and we considerably limit the role of the fluid by studying pairwise lubrication interactions, as in those papers by Melrose and Ball I mentioned earlier. And but considering what happens if we only consider this lubrication effect, that is to say the coefficient diverging as 1 over the distance between two particles with smooth surfaces, coefficient relating the force to the relative normal velocity, considering what happens, namely that we see extremely small gap thicknesses, even smaller than the molecule size. Well, we have to cut off the singularity, accounting for the existence of asperities on the particle surfaces. And due to those asperities, lubrication will not apply any longer. The lubrication effect will not apply any longer. So particles will touch in a finite time. So there is a there's a lubrication cutoff. And well, that's one ingredient of the model. Or we might as well consider a short-range repulsion due to some polymer layer adsorbed or grafted on particle surfaces, as some people do to stabilize colloidal dispersions. So, and I will limit my study, as opposed to what was done in previous presentation, to the Stokes regime. There's only viscous forces in the system. There is no inertia whatsoever. And I try to approach the quasi-static limit within the Stokes regime. Only viscous lubricating forces. Now I will then review the investigation we've been able to do of those issues, divergence of the viscosity, sensitivity to various features of the model. Okay. So quickly, the basic ingredients of the model are those force laws. So viscous force. This is the lubrication singularity. H is the distance between two particles. So this is relative velocity. This is normal viscous force. And these are supposed to be the dominant hydrodynamic forces, and this is the reason why we keep only those. So ignoring filtration and flow of fluid relative to particle network. So to allow for our contact in a finite time, we cut off the singularity like that. There are other ways to do it. This is very much an ad hoc feature of the model. You can decide that the divergence is here, for instance. We use this cutoff, and this is supposed to be assumed to be related to asperity size. Well, without cutoff, as I said, it's both physically irrelevant and computationally untractable, because you have 1 over h reaching values that are just too high, and physically it's too small a distance to make sense. Now, well, all those ingredients of the model are not equally interesting, but we fixed the cutoff to various values between 10 to minus 4 and 1/100th of the particle size. We kept in contact forces with a stiffness level quite high, so that elastic deflection will be negligible in practice. And then we define, oh, I hope it's defined. Yeah, well, it's not. Okay. We try to approach the quasi-static limit and to explore the range of behaviors for various values of this viscous number, which I forgot to write before, but which somebody, various speakers already used, and which will be written further down in a while. And so we try to approach those systems with a quasi-static limit that is presumably the same critical state. We would to characterize this approach to the critical state. That should be the same as in dry grains. That's the idea. So we, as you know, the number of particles is relatively modest, and we have frictionless beads in 3D and frictional grains in 2D. So we are trying to be realistic, but we have to limit our ambitions because of the numerical difficulty of the problem. So now the method is just like this. I have a few slides on the computational method that, well, after all, we might discuss those aspects too. So we have to work with the hydrodynamic resistance matrix, which gives us the viscous force as a function of the velocity vector that contains all the velocities of all the particles, including if there are tangential forces, including the rotational velocities. So all this depends on grain position, and we have to solve a linear system of equations that's like this, with contact forces and externally applied forces. That's how we exert stress in our system. Some technical aspects furthermore. So we have to, as much as we can, avoid wall effects. So we use periodic boundary conditions. It's called Lees-Edwards boundary conditions in numerical literature. And this cell also has a variable height, so it ensures a constant pressure. That's how we control the pressure. And we have to wait for stationary state and all that. An interesting and physically important feature is the regression of fluctuations. If we so we measure density and we measure stresses, so internal friction, and we have to make sure that the fluctuations on the curves regress if the system size increases, and that's what is shown here. And furthermore, it shows that the importance of fluctuation about the average value decreases with the traditional scaling as the number of particles to the power -1/2. Okay, so this is encouraging, and this also tells us that the limit should be well behaved. It should be a good constitutive law, but because if the fluctuation really the fluctuations really regress, it means it won't change anything. It's eventually in a very large sample if we completely fix the density. So constant volume, constant shear stress, constant normal pressure, all different kinds of controls should lead to the same macroscopic law, except that, of course, normal pressure is more convenient. Well, there are issues of time step and integration. Maybe I skip that one. This is a funny thing we should pay attention to occasionally. There are traps in the simulation of those systems. It's a little bit tricky. The lowest order algorithms we might think of is first order. So if we compute step by step the trajectories to first order in the velocities, just consider that this displacement is velocity multiplied by time step. And particles tend to move tangentially to one another because it's so hard to approach due to this lubrication effect. So in a tangential motion, then to second order, particles move away from one another. Spheres move away from one another. And this can lead to spurious results. Here, if we compare, if we want to study the distribution of interstices between particles, there are two ways, of course, to look at them. We know the position, so we measure them as functions of time, but we also work with normal velocities. And if we integrate the normal velocity, well, this tells us how much the distance between the particles should vary. But if the two calculations do not agree, then we have a problem. So here is just a test that is suggested as a quality test for simulations of dense sphere assemblies in a viscous fluid. So with two algorithms of different accuracy, we see, considering some pairs of neighboring particles in the system, how the two calculations differ. This is the relative error here. So the dotted lines correspond to the lowest order algorithm. We see that while the gap thickness is 1/1000th of the particle diameter, while in quite a few examples, we see that the error grows in an unpleasant way. So we use this algorithm and we limit ourselves to situations in which typically this does not exceed 5%. Otherwise, we're doing inconsistent things. Now, here is our viscous number. Sorry, it did not appear before, but it carries no surprise now. We all know it. So it's, of course, the ratio of two characteristic times. It's the shear time divided by the time you need to squeeze a lubricated interstice between two neighboring particles. Maybe it's the opposite ratio. No, it's the, squeezing time divided by the shear time. So, well, you might justify differently the definition of such a number. And now is a comparison between constant normal stress and constant density. So well, this is dense suspension. Results are always not as beautiful as with dry granular materials, but it does show that here, if we switch from fixed normal stress to fixed density control, the level of fluctuation of stresses, individual stress components, in that case the shear stress, shoots up. These are very strong fluctuations as opposed to the previous situation. While the density, which is now fixed, solid fraction which is now fixed, was only moderately fluctuating before, between 0.615 and 6.2. So, same phenomenon, same interest, same justification for turning our attention to stress-controlled simulations. Now, solid, internal friction, solid fraction versus viscous number. Well, similar results as for dry grains, in which case it is versus inertial number. But the bad news here, I'm sorry, is that we're not approaching the quasi-static limit close enough because, well, we probably would need to go to smaller viscous numbers, and then we're confronted with the numerical difficulties I mentioned, that the integration scheme loses its accuracy, and it's more or less, it takes a tremendous lot of computer time. So we should approach this, which we might believe, but which is not absolutely proven by this numerical study. Here is a comparison between two cutoff distances with the idea that we would like to, what we neglect in the hydrodynamic interactions, we would like it not to be too important. So if we introduce more hydrodynamic interactions, it doesn't change the result much. That is a good sign. Now, of course, we might go back to traditional approach, in which case the viscosity is the quantity that is measured. So to do it, we transform our data like this. We consider the shear stress divided by gamma dot, and combining things, we end up with this expression here, telling us that what matters is the distance of the solid fraction to its critical value. So we have here the traditional divergence of the viscosity as the maximum density is approached, and this maximum density, we argue, is the density, is solid fraction at the critical state, the quasi-static shear flow, plastic shear flow. Now, this viscosity in that case can be shown to be independent of shear rate. Well, numeric dimensional analysis tells us it is a function of those dimensionless parameters here. And this one involves the stiffness of the particle interaction at contacts. And as we work in the limit of large stiffness, this argument goes to 0. So nowhere, gamma dot is nowhere to be seen in the remaining 3 arguments. So it should be a Newtonian fluid. Of course, this exponent, we would like to measure it accurately, but as we need mu star to 3 minutes, okay. As we need mu star to approach this limit, we're not quite there yet. Now, this is our viscosity diverging. Okay, maybe I'll skip those study of repulsive forces. I'll show you the case of, okay, I would like to show you this. Check on the accuracy of the computation with the viscosity of random isotropic suspensions. Random isotropic suspension, you know, it's not the flow structure, it's just the ideal hard sphere distribution in space. And then if we compare with a more accurate Stokesian dynamics approach, we see that there is a fairly good agreement. So it's encouraging for the accuracy, quantitative meaning of our results to some extent. Now we turn, because of those difficulties, we turn to 2D disk model in which we introduce friction in the contacts. So the simulations are very, very similar. But now what changes is that the approach to the quasi-static limit is easier, because it's always easier if we have friction to dissipate as an additional source of dissipation. So what is shown here is the macroscopic friction coefficient versus viscous number, which approaching the quasi-static friction coefficient, which is the same as in the dry case, for the same intergranular friction coefficient here. not for 0, for 0.3. And those two curves of different colors correspond to different size for asperities or cutoff of the lubrication singularity. Yeah. And we see that the quasi-static limit is the same, but the curve is not the same. So same thing for the density this time, approach of the critical state density, which is the same in the viscous suspension case and in the dry granular system case here, that value here for the same intergranular friction coefficient. Slightly different curve too. So dependence on this feature of the model, asperities size. Well, the exponents are not fascinating. I'll skip that. Also a divergence of the viscosity, but similar difficulty to identify the, oh, I'm dead, to identify the exponent. It's between 2 and 2.5 maybe. That's not extremely accurate. Dominance of the contacts, pressure due to the contacts divided by total pressure as we approach to the quasi-static limit. So some conclusions, it's about right. Some conclusions. I've been arguing in favor of the study of dense suspensions and the controlled normal stress. I've stressed the importance of contact interactions because this the solid friction determines the density, the density at which the viscosity diverges. So this is yet another example of the relevance of the critical state concept. There should be, I've argued that there should be nothing funny happening below random close packing density if particles have no friction, because the critical state density is the random close packing density then. Okay. Yeah? Okay, these are my perspectives. This is the one that summarizes many others, I think. This is the aim. Thank you for your attention.
We have one question maybe while the next speaker comes up.
Yeah. So for hard particle systems, for compressive stresses, it diverges at 64% random close packing. And under shear,
Excuse me, I didn't understand the beginning, so I'm in trouble.
For hard particles under
Yes.
compressive stress,
And the compressive stress.
the pressure will diverge at random close packing.
The pressure would diverge at random close packing. Hard particles, but
But for shear, it diverges at a lower volume fraction.
I don't understand. Are they Brownian or whatever?
No. Dry granular particles, hard particles, under shear, they will diverge at a lower volume fraction.
If they have friction?
Even without friction.
No, I don't agree with that statement.
I'll show you.
Okay, you can shear hard particles up to random close packing.
Athermal.
Hmm?
Athermal. Athermal hard particles.
Yes, athermal hard particles.
We should discuss that.
Yeah, well, that's the result on dry grains too. Okay.
Yes.
Okay. We will discuss that point.
Okay, let's thank our last speaker.